Hello and welcome to this brief presentation related to scalar and vector quantities. As you'll see, scalar quantities have a magnitude only and vector quantities have a magnitude and a direction. Let's consider scalar and vector quantities. Within engineering, it's important to know which quantities are scalar properties and which are vector properties. When adding or subtracting vector quantities, account must be taken of their direction, or else the final result will be incorrect. Let's first consider some common scalar quantities used in engineering. They're shown on the next slide. So scalars are quantities having a magnitude, that's a size, but no direction. So such quantities include mass in the SI system measured in kilograms. So a piece of equipment is 2,000 kilograms, or sometimes written as 2 ton. That's the magnitude and no direction associated with it. Distance in meters in the SI system. So a machine tool travels 0.75 meters or 750 millimeters. Again, that's a magnitude, there's no direction. Area in meters squared in the SI system. So the surface area of a washer, for example, is 0.282 times 10 to the negative 3 meters squared. Volume in meters cubed in the SI system. So a storage tank has a capacity of 25 meters cubed. Again, that's a scalar quantity. Speed in meters per second in the SI system. So an aircraft takeoff speed of 42 meters per second, or converted to 151 kilometers an hour. Both are scalar properties. Note that scalar properties can be positive or negative. So for example, temperature. A train wheel is cooled to negative 23 degrees C. That is a scalar property, but it's a negative scalar property. In the SI system, temperatures are measured in Kelvin. So adding 273 to the degree C temperature, we find in Kelvin that's 250 K. We review the Kelvin scale in other presentations. Time in seconds in the SI system, so the periodic time is stated as 0.05 seconds or 50 milliseconds, again scalar quantity. Power in watts in the SI system, so a generator rated at 5,000 watts or 5 kilowatts, again scalar property. And energy in the SI system measured in Newton meters or joules. So a system change of energy is negative 1500 joules or negative 1.5 kilojoules. Again, that's a scalar property. Let's now consider some common vector quantities used in engineering. So vectors are quantities having both a magnitude and a direction. So displacement in meters. Notice on the previous slide we considered distance in meters. Distance is a scalar quantity, displacement is a vector quantity. So an example of displacement is 12 meters to the northwest. The 12 meters is the magnitude and the northwest is the direction. Velocity measured in meters per second in the SI system. And again, on the previous slide, we considered speed as a scalar quantity in meters per second. Velocity is a vector quantity in meters per second. So for example, a velocity of 30 meters per second on a bearing of 070 degrees. The magnitude is the 30 meters per second and the direction is the bearing. Acceleration, unit of meters per second squared in the SI system. So an acceleration of 0.05 meters per second squared upwards. A magnitude 0.05 meters per second squared and the direction is upwards. So forces measured in newtons in the SI system. So for example, a force of 5 kilonewtons applied along the axis of a tie bar. Again, the magnitude is the 5 kilonewtons. The direction in the context of the question would be along the axis of the tie bar. Weight or weight force, also measured in newtons in the SI system. Weight is a specific type of force. We reviewed this in a previous presentation related to SI units. So, example of weight, 700 newtons acting vertically downwards. Remember, weight force is a specific type of force. It acts in one direction, and that's vertically downwards. And momentum. In base units in the SI system, momentum would have the unit of kilogram meter, but it can also be specified as Newton seconds. Again, we review this in a later presentation related to momentum. So, for example, a momentum of 30 Newton seconds horizontally to the right. Again, we have our magnitude, 30 Newton seconds, and our direction, the horizontally to the right. Let's now consider some examples of various applications of vector properties in particular, although I'm commencing this slide with a scalar quantity. This is an image I found drawn on a whiteboard after I'd left the classroom for a few moments. It's a cartoon image of me in a hangman position. You can see I'm very popular with my students. But we're using it here to illustrate the quantity of mass, symbol lowercase m, and mass of course is measured in kilograms. So mass is a quantity of matter. We cannot draw any arrow associated with the mass because mass is a scalar property and they have a magnitude, so a value in kilograms, but no direction. If I'm now considered in a gravitational field, like on Earth for example, gravitational acceleration, symbol g, is assumed to be 9.81 meters per second squared. Acceleration is a vector property, so I can draw a downward arrow to show the direction of the acceleration. We want to calculate my weight force or my weight. In the SI system that will be in newtons. Then we know that weight is equal to mass times gravitational acceleration shown above. And as weight force is a vector property, we can now draw an arrow, a downward arrow in this case, to indicate the direction of my weight. So there's a contrast between a scalar property, mass, and a vector property, weight. Just a few slides now to show you typical examples of a vector quantity. So forces we mentioned are vector properties. So in engineering we sometimes construct a triangle of forces. In this case we have two forces applied to an object. We have a horizontal force shown here of 10 newtons and the force at 45 degrees to the horizontal shown as 5 newtons, and we can draw a force vector diagram to find the resultant force. So the horizontal force is 10 newtons, drawn from left to right here, and then the 5 newton force is drawn on the end of the 10 newton force. So we can calculate what's termed the resultant force from our vector diagram. So this shows a clear example of a vector property, a force of 10 newtons acting horizontally to the right here. We can draw that on a vector diagram to some scale. And again, another example of a vector quantity, but a polygon of forces drawn here. It just means we have more forces applied to an eye bolt in this particular case, or actually 4 forces applied to the eye bolt here. And we can draw a vector diagram, what's sometimes termed a polygon of forces, as shown here. And from this we can find the resultant force on the eye bolt. We review these force resolutions in a separate presentation on graphical representations of forces. The point I'm trying to make here is that forces are vector properties and we need to not only account for their magnitude but also their directions. Directions here are given in terms of the angles to the various axes. Another example of a vector quantity, of course, is velocity. Velocity in meters per second. This illustration relates to two aircraft flying in different directions. We're given a direction of the Boeing aircraft. We're given a direction of the Airbus aircraft. And this particular question, we're trying to find the relative velocity of the Boeing aircraft to the Airbus aircraft. So again, we can draw a relative velocity diagram. What I'm trying to highlight to you here is that we are using the directional properties of the vectors to calculate the relative velocity shown here on the diagram. Another example of a vector quantity here is momentum. In this particular question, we're given the velocity, which itself is a vector property of a component, and we're asked to find momentum in that direction. So again, we can draw a velocity vector, 2 meters per second in this particular question, and our momentum vector, because both velocity and momentum are vector properties. Again, momentum is reviewed in a separate presentation. Another example of vector quantity here is momentum, but used in terms of collisions when we have two objects colliding with each other. Again, we have to account for the directional sense. So your two vehicles before impact shown here, one's travelling from left to right, 50 kilometers an hour, one from right to left, 30 kilometers an hour, and we're trying to find the velocity after impact. So again, you can clearly see we're accounting for the directions of the velocities here when we consider the conservation of momentum. And again, the topic of momentum is considered in a separate presentation. And a final example of a vector quantity, in electrical work, we often refer to phasors. They're actually defined as rotating vectors, so they're considered like vectors. And sometimes we want to find the resultant force of two voltages, for example. Got a voltage shown here horizontally, 3 volts, and a voltage shown here vertically of 2 volts. And we can draw a phasor or vector diagram to find the resultant force of the two voltages. So in electrical work also, we use this vector property to help us solve particular problems. So that's just a very brief introduction to scalar and vector properties. I hope this has been of interest to you, and thank you for viewing.